programs.
Okay. So hi everyone. So this is the joint work with Quantum and then CMU. So given first what is static resource analysis? So given the program P and static resource analysis, answer the question: what is the amount of resource as time, memory, allocation, or energy consumption as function over the input that it is required to execute program P. So the goal of the resource analysis is to help developer answer this question and analysis of the programming language support. So there are many techniques that can be applied to reason about the resource usage of program, and they usually provide the upper bound on the worst case resource usage of program. For example, one of it is automatic multi-resource analysis here. So in this work, so we are working with probabilistic program. So what a probabilistic program? So they are the functional or imperative program with two added control. So the first one is sampling assignment. So to draw a value at random from probability distribution. And the second one is probabilistic branching to use to control program flow by observation. And we could think that programs are probability distribution, right? And here are some probabilistic programming language in practice. So for example, probabilistic C or the PyMC3 is a third library of Python language, and Figaro or Edwards. Okay. So let's consider a random worker here. So where X is the current position of the worker and N is a boundary condition. So meaning that the worker will stop working when he reaches this position. Okay, X unit of time. So the workers go forward one step with probability 0.75 and go backward one step with probability 0.25. So we can simulate this random work algorithm as a simple probabilistic program. Here, notice here I use Python's line syntax to write program. So here we are interested in the working time of the worker here. So that means in other words, it is the number of iteration of this loop, right? So it is the cost of the program here. So the worst case cost, it is clear that so the worst case cost is infinite. So it does not make sense to reason about the worst case cost here, right? So it is better to reason about the expected value of the cost here, or we can reason about the probability that the cost is bounded by a threshold. So in this talk, so we will talking about the automatic bounds on the expected cost here. Okay, so maybe it could be a homework for you to compute what is the expected value of working time for this program. Okay. So why we study the expected resource usage? So first, there are many interesting applications. So for example, we can use expected resource usage to predict the expected resource usage of sampling in probabilistic inference algorithm. Or we can use it to reason about the average complexity of randomized algorithm, or reason about the positive and almost sure termination of probabilistic program. Okay? And second, it is a technical challenge problem here, because if you think about how to manually analyze the expected resource usage of probabilistic program, so it turns out that it is very difficult or impossible in practice. So another thing is that so there are no techniques that automatically infer symbolic bounds on the expected cost now. Okay. So our techniques called expected potentials method. So it combines a Wicked-Bree expectation calculus. It is a kind of Wicked-Bree condition style, and an automatic amortized resource analysis. So our technique research the best probability of both worlds. So on one hand, it can have the strength and conceptual simplicity of the WP style calculus, and it can have a soundness with respect to a simple operational semantic. On the other hand, so it is based on the template-based bound inference, and it can be automated efficiently by reducing to the LP solving problem, and can be solved automatically by a LP solver. So as a result, so our expected potential methods can automatically infer bounds on expected result usage for probabilistic program, and the bounds are multivariate symbolic polynomials. And it also enables compositional and effective reasoning. Okay. So let me talk about the key idea of the expected potential methods. So the first, for each program point, so we assign a potential function. So a potential function is a function from program state to the non-negative value. So here we call the phi. Okay. And second, so we use the potential to base for the expected result consumption of the command, the executing command, and the expected potential over distribution of next state at the following point. So that means the potential at the before the command and after the command satisfies this condition, right? And then by the law of total expectation and the linearity property of expectation, the phi the unit potential function is an upper bound on the expected result usage of the program. Okay. So it turns out that so we can use a whole tuple to represent the relationship between potential function here. So here, so phi is the result available before executing the command C. So C can be the deterministic command or probabilistic command. Okay, and E of phi prime here is the expected result available after execute the command C. So the intuitive meaning of this tuple is that so for all state sigma, so the phi sigma is sufficient to pay for the expected cost of executing the command C, and the expected result available after the execution with respect to the distribution over the next state here. Okay. So here I give you a flavor of the inference rule in our derivation system. So the gamma here is a conjunction of logical assertion that hold at the current program point, and for example here for the probabilistic branching command, so the init potential, the potential at the beginning of the command is a weighted sum, and we can encode at a linear constraint in our system. For the sampling assignment, so we require that so the distribution R here decrease with finite domain. Okay. So let me go back to the random walk example. So we want to derive the bound 2 mark 0 n minus x at the upper bound on the expected working term. Okay. So we reason backward with the potential function 2 mark 0 n minus x at the end of the tix1 command here, because the tix1 consumes 1 result unit. So we note that we also prove that so this potential function is also a loop invariant. Okay, because the tix1 here consumes 1 result unit, so we before the tick command or at the end of the probabilistic command here, so we need this potential function 2 mark 0 n minus x plus 1, because we need 1 here to pay for this computation, right? And because the next one, so we execute the assignment x equal x plus 1, because this assignment trains the program state, so we have to transform this potential function to account for this. So we transform this potential function into this potential function. So you can check that if you replace the x here by x minus 1, so you can obtain this function, right? Similarly, for the second assignment x equal x plus 1, I have to transform this function into this function. Okay, and because I execute this assignment x equal x plus 1 with probability 3 over 4, and I execute this assignment with probability 1 over 4. So I assign this potential function at the at the beginning of the probabilistic branching command here, add the weighted sum of this function and this function, right? So, and also because here I have this potential function, and because the evaluation x smaller than n doesn't change the program state, so I can use the same potential function here. So that means I have an atomic loop invariant here. So we can conclude that. So this is an upper bound on this expected result usage of this example. Okay. So, and also this number should be the exact expected cost of the working random work program. Okay, you can, so it is, so note that it is again the homework, you can prove that. Okay. So in order to automate the annotation above, so we do the following step. So first, we fix the potential function as linear combination of polynomial. So in which the monomial can be the constant function 1, a variable, or the product of two monomials, M1, M2, or the mark operation here. Okay? And here the Ki is the unknown coefficient. And which we try to find out what is the value of the Ki here. Okay? And the second step, so we encode the potential generation bit at the current and the next program point as a linear constraint. And finally, so we obtain the optimal solution. I mean the minimized solution by solving the generated constraint with an off-the-shelf LP solver. Okay. So let me give you another example, the funding example here. So let's say that we have a clip of doom and a bit of disaster, and we have a bug here. So the clip of doom at the position 0, and the clip of doom at position 0, and the bits of disaster at position W inches. And we have a bug at position N in between. So the bug will repeatedly hops one link to the left or right with equal probability. So we can implement this example at a simple, at a loopy probabilistic program like this. Okay, and so we are interested in the knife of the bug. So that means it is the number of hops in the loop here. So our analysis will infer a time nonlinear bound for the expected knife of the bug is mark 0 and n multiplied by mark 0 w minus n. Okay. So it is a derivation of the bug life example. So this is a derivation of the bound, and this is similar to the one in the previous example. So the potential function here at the beginning of the probabilistic branching command is the weighted sum, in which the term with degree 1 here, they are cancelled out because of the equal factor. Okay, and we think that, so if I can prove that this one also the null bound of the expected cost or the expected life of the bug. And we think that if the right side is not bounded, so for, meaning that the W goes to infinity, then the bugs will live forever expectedly. Okay. So let's talk about the implementation. So we build a tool called Epsin. So that accepts imperative integer probabilistic program, and it can infer multivariate polynomial bounds on the expected resource consumption. And we also evaluated our tool on 40 challenging probabilistic program and randomized algorithm with different looping patterns. And we also compare our derived bounds with the simulation by expectation to show that the content factor inside the derived bounds are very precise. So this chart shows that the tool derives bound in less than 10 seconds for all program in our benchmark, and the error between the simulation by expectation and the derived bounds are less than 1% for almost program in our benchmarks. So, for example, this figure shows the content factor in the derived bound for random walk and the polynomial program very precise. So in the figure, is the blue lines are plotting of the derived bound. Okay, yeah, yeah. And the red point are simulation by value. So we see that, so they are very tight together. So here we saw that, so the expected this sort analysis can be used to reason about tail bound probability with the use of the concentration inequality. For example, the Markov and Chebyshev inequality, because the tail bound assert that the this sort usage is bounded with a high probability, so they are good for analyzing the safety probability of program, right? So for example, we apply the Markov inequality for the random walk example here. So let me conclude. So this works present the first automatic analysis for deriving symbolic bounds on the expected result usage probabilistic program. And it also provides a practical implementation for imperative probabilistic program. Okay. However, there are some limitations. So for instance, it cannot reason about the non-polynomial bounds, expected result usage. And the current implementation only supports discrete distribution with finite domain. So for future work, so we want to reason about the narrow bounds on the expected result usage and the tail bound analysis with Chebyshev inequalities. So thank you, and I'm happy to take questions.
Any questions? No? Okay. So I have two questions.
Yeah.
First one may be somewhat naive. So in one of your examples with the bug, you derived non-linear constraints. How can you do that when your templates are linear?
No, actually the template is not linear because you see that the monomial, it can be product of two monomial, right? Okay.
Okay, and well, the second question, I work with floating point numbers and you have integer programs, so could you extend your technique to, let's say, real valued probabilistic programs? Would that cause any trouble?
Because I think that the trouble comes from two sources, because the LP solver, so somehow it can reason about the constraint with the rational value, right? It's not real value. And the second thing that if you look at our inference rule here, so we simulate the simple assignment, the rule for simple assignment at the rule for probabilistic branching command, right? So because if we need to compute what is the probability such that the sample of the distribution R is the value VI here. So that means that if we want to support for example, the real value for continuous distribution here, so that means maybe the domain is infinite, so we cannot apply the Q simple rule here. So maybe I don't know how difficult we can deal with that. But
okay.
Hi, do you think your tool could be extended to give exponential tail bounds using Chernoff's inequality, for example?
I think it is possible, because if you look at the syntax of the monomial here, I don't know. Yeah, so the syntax of monomial here, if I can extend the syntax of monomial with something to deal with the exponential here, for example, the E of P or something here, so I think that so the analysis can derive the exponential bound.
Okay.
Any more questions? Okay, if there are no more questions, let's thank the speaker again.